Hello, we're going to talk about the method of cylindrical shells. There we go. We're going to talk about the method of cylindrical shells, which is another method of computing volume. We've already discussed integrating the cross-section, particular case where you have the cross-section is circular because you have a solid revolution that you revolve around the x-axis. That's the disk method. We've also talked about the washer method, which is basically the disk method that's been punctured. Now we're going to talk about cylindrical shells, which is more useful when you have something that's being rotated around the y-axis. Okay, so I'm going to go to the writing mode and we're going to discuss that now. So the method of cylindrical shells is most useful when you have something being revolved around the y-axis. So I want to insert an x and y axis. There we go. So let's say that you have your f of x looks like this, and you're integrating, or you have this area here from a to b. Oops, I cannot write today. And what you've done, hopefully this will make sense, is that you've revolved everything around the y-axis. So that's been that point at A has been revolved around the y-axis, and then here we'll revolve around over here at B. Whoa, okay, that looks weird. There we go, that looks a little better. Let's change this. So you get something that looks sort of like this. So it gets revolved around, and the shape of it looks like that. Okay, so this has been revolved around like so, and then you have the top looks something like this. Okay, so you're revolving around the y-axis. Now, let's see if I can solve that. Explain how this is going to work. Sorry. So, what we've got is should still set this up like a Riemann. Well, here, let me draw this first. So let's just choose a point right here. So this is going to be our point right here, xi. So I've made this, what's it called? A rectangle. Let me thicken it up a little. This one right here in white. So looking at this rectangle, it has a width of delta x and it has a height f of xi. Okay, so the area of this rectangle equals the width times the height, which is f of xi times delta x. Okay, now you can imagine that this rectangle is going to be revolved around the y-axis. And you can see why it's called a cylindrical shell, because when you revolve that rectangle around, you don't get the whole cylinder, right? This part here in the inside is left out, which is why it's a cylindrical shell. Okay, so let's compute the volume of this thing. Well, you're going to have the volume of the outer cylinder minus the volume of the inner cylinder. So the volume of the outer minus the volume of the inner. So, what is the volume for a cylinder? Well, it's let me think. The volume for a cylinder is the base times the height, and the base is pi r squared times the height, which is h. Okay, so the volume of the outer one is going to be pi. Now, the radius here is xi, because the radius is being measured from the y-axis. So you get pi xi squared times the height is f of xi. The height, the volume of the inner cylinder is pi. Now, if you look at the little rectangle, you have xi right here, and now because the other point is a distance of delta x away, you get xi minus delta x. So you get xi minus delta x quantity squared times the same height, f of xi. Okay, so looking at that, you realize that you can factor out the pi f of xi, and then that will leave you with xi squared minus xi minus delta x quantity squared. Okay, so we could go and multiply this through. Let's do that here off on the side. So let's expand out the xi minus delta x quantity squared. That's going to be xi squared minus 2xi delta x plus delta x quantity squared. Okay, so as we multiply this through, we're going to get pi f of xi times, now the xi squareds are going to cancel, and then when you distribute that minus, this minus will become plus, and this plus will become minus, which will leave us with 2xi delta x minus delta x quantity squared. Okay, which we can then distribute, and we get 2 pi xi f of xi delta x minus 2 pi f of xi delta x quantity squared. Okay. Now, if you think about this in terms of infinitesimals, whenever you have the infinitesimal, like a delta x squared, that term goes to 0, so you can just ignore this. Because the idea is that delta x is a small value. It's like the smallest that you could detect in some sense. So when you square something that's practically 0, it gives you 0, which means you're left with 2 pi xi f of xi delta x. So that's basically the volume of one of these shells. Okay, so if you wanted to find the total volume, well, or if you're going to estimate the volume, you're just going to sum those. So you'll do the sum from I equals 1 to n of 2 pi xi f of xi delta x. And then if you wanted the actual area, you would take the limit of this. So you would take the limit as n goes to infinity of sigma I equals 1 to n of 2 pi xi f of xi delta x, which, because we're integrating from a to b, what you get is ab 2 pi x f of x dx. And the way you want to visualize this is like so. Okay, so if you have this function f of x, and you're integrating from A to B, and you're revolving everything around the y-axis, what you're doing is, this is some x value right here. That's practically speaking your radius. And then as you rotate this around, 2 pi x is the circumference as you rotate around the y-axis. You might remember that the circumference of a circle is 2 pi r, right? So your x is the radius from the y-axis, that's what you're revolving around. The f of x is the height. So it makes sense, your circumference times the height basically gives you an area, and as you integrate that area, you get the volume. Okay, so we'll do some examples. So example, calculate the volume formed by revolving f of x equals 1 over x around the y-axis on the interval 1, 3. Okay, so you have your 1 over x. It looks something like this. You're going from 1 to 3, so you're revolving that around. So you get this shape that sort of looks like this. So hopefully you can sort of see it. That's the 1 over x part, and then you get this like, okay. So you get that shape like that. So let's set this up. So I'm gonna choose a rectangle right here. This point is gonna be my xi. So the area of that is what is it? It's f of xi times delta x. Or actually, I guess we should just jump into the formula for this one. We know that we're gonna have the sum of I equals 1 to n of 2 pi xi times f of xi delta x, where xi is that radius as we're going around, so that's still the xi. The f of xi that's determining the height is our function 1 over x. So as we plug it in, we get the estimated area is sigma I equals 1 to n of 2 pi xi times 1 over xi delta x. These are going to cancel, so you get the sum of I equals 1 to n of 2 pi delta x. So we know that when we take the limit of this, we're going to get an integral from 1 to 3 of 2 pi dx. The antiderivative of that is just going to be 2 pi x. So we're going to want f of 3 minus f of 1 by the fundamental theorem of calculus, which is going to give us 2 pi times 3 minus 2 pi times 1. If you factor out the 2 pi, 3 minus 1 is 2, so you get 4 pi. Cubic units of volume for that shape. Okay, so remember that what we're thinking, how this is working is you're taking this rectangle here, and then you're revolving it around, right? So you basically get the outer cylinder minus the inner cylinder. You could go through that whole calculation like we did up here. Remember, if you do that, the pi square, the delta x squareds are going to just disappear. But you can just jump into setting up the estimated volume and then taking the limit, which gives you the definite integral. And that is the method of cylindrical shells.